All right, guys, welcome back. Thanks again for tuning in. Mr. Ray here with some more for you on chapter 2. We are looking at probably one of the most important parts of the early part of the year. In chapter 2, we are learning about what's called the normal distribution. And the normal distribution is the distribution we know so much about. And it's one you've probably heard of before. You've probably heard of teachers talk about the bell-shaped curve when they're doing grading or something like that. And that's what we call in statistics the normal distribution. And so I'm going to do a little work here on the virtual whiteboard, but then we are going to be doing some work with some actual paper and pencil today. So if you don't have a piece of paper and a pencil handy, now might be a good time to pause the video and go get it. We're going to do a little construction later. So you'll want a blank sheet of 8.5 by 11 paper. If you have like a piece of printer paper or something like that, that will work great. I'm going to help you with something in just a little bit here. So the normal distribution. The normal distribution is what you have probably heard of is called the bell-shaped curve. So I'll draw one out here as best I can on this thing. And the normal distribution, it covers so many things, so much data is distributed according to this distribution that it really is deserving of its own whole section here. And so that's what we're going to look at today. Is what do we know about the normal distribution, some features of the normal distribution, and then some things that we can learn once we know things are approximately normally distributed. So this is the normal distribution. And here are some key components or characteristics of the normal distribution. The first thing is the mean. Now I'm going to use the Greek letter mu because this is about a population. And when we have the mean, I know earlier we did X bar. That's a sample mean. So when we have a sample, but if you have a population, you use the Greek letter mu. Okay, so I'm going to call this center line here mu. In a normal distribution, this is also the median. So this is also the median. And the height of this curve represents frequency. So that is the most common. So this is also the mode. Mean, median, and mode are all the same thing if something is distributed normally. So kind of a fun fact there. Standard deviation. Well, in a sample, right, that we used a S for our sample standard deviation. Okay. In a population, we use a lowercase sigma. Okay. And if you notice the curve here, now I apologize for it not being perfectly symmetrical. They are supposed to be symmetrical. In the middle here, you can see how it kind of curves down. It's kind of curving down like a frown, like in here. Okay, but then out here at the sides, it's actually curving kind of up like a cup over here, up here, and up out here, but down in the middle here. Okay. Well, there's a point where the transition between up and down happens. Okay, now if you've had calculus class, you know the name of this point here, and there's another one over here. Those are called inflection points. Now, don't worry if you don't know what that means. Just know that it means the transition point between where it's curved up to where it's curved down. The interesting thing about the inflection points in the normal curve is they are exactly one standard deviation away from the mean. So those distances there in theory are the same. I know my drawing's not to scale, guys, sorry. Those distances are exactly one standard deviation. So if you were to subtract 1 sigma, you'd get to this value here. If you were to add ooh, boy, that's not a very good sigma. If you were to add a sigma, you would get to this one right here. And those are also some interesting features of the normal distribution. It comes down and it gets really close to the x-axis down here, but it never actually touches. Okay, so the x-axis is what we call an asymptote to the curve. Okay, we get really, really close to the curve. I'm sorry, the curve gets really, really close to the axis, but it never touches it. And so what that means is there's always a little bit of area in there. Okay, there's always a little bit of area under the curve. And so the area under the curve idea is going to become a big deal for us in a little bit here. Things that are normally distributed will then, in theory, always have a frequency that fits underneath this curve, which means as you try to fit this curve to something that's kind of real, it can lead to some pretty bizarre ideas. Meaning like, you know, you could go way out here to the right, all the way up to, you know, positive infinity, saying like, you know, if you pick something that's normally distributed, like in the US, the height of US women is approximately normally distributed. And so if you were to take the height of US women and look at the normal distribution, okay, normally we would write, we would put like n mu comma sigma. Okay, so for US women, normal, okay, 64 comma 2. Now we're talking in inches here. It follows a normal distribution with a mean of 64 inches and a standard deviation of 2 inches. But because this curve never touches the x-axis, that means in theory, right, according to the normal curve, a woman could be, let's say, 100 inches tall. But there's such little area underneath here that eventually we say, okay, that's not really possible. There is a small likelihood that it could occur, but in real life, we know that 100 inches would be a little extreme. So, so there's a point at which the normal curve becomes no longer very realistic for describing the situation that we might be looking at, and that's one of the weird things about it. So, but it does work so well for lots of different distributions. The height of US women are in fact approximately normally distributed, and the mean is 64 inches with a standard deviation of 2 inches. And so we'll actually use that data or that normal distribution quite a bit as we go through. So that's the normal distribution right there. So what I want to look at here are some more characteristics of it. And to do so, we're gonna make a foldable for this. So I'm gonna transition over to my document camera. If you didn't have a piece of paper yet and something to write with, now is the time. So you'll want to pause the video. And what we're gonna do is we're gonna start by doing what's called a hot dog fold to our paper. So I'm gonna fold it hot dog style, like so. And now here's the tricky part. I want to fold this so that I get 5 creases, 6 windows here as I go across. Okay, six little rectangles. Any ideas? Okay. If you said fold it into thirds and then fold it in half, you would be correct. To fold into thirds, fold the top part down until you get two equal sized rectangles here. Okay, this one and this one should be about the same. Okay, you can fold the bottom one up. Oh, I didn't quite get it. Didn't quite get them to be the same, did I? No. Well, you get the idea. Mine aren't going to be very evenly spaced. Sorry, guys. All right. And then once you have your thirds folded, then just fold that in half. Okay. so that when I unfold this thing, I should get 1, 2, 3, 4, 5 creases. 1, 2, 3, 4, 5, 6 windows. All right. Now here's the thing we're gonna do. I've got some scissors here, and we're gonna do some cutting. I'm gonna cut this crease, just up to the middle there, this crease, and this crease. Do not cut that crease right there in the middle, okay? We want that one to stay whole, okay? So what I'm gonna do is cut just like this. And you can see, I didn't cut underneath, that's still there. I just cut halfway across. I'm gonna do that for all of my windows here. Okay, so if I open it up, okay, I should see that I've got, you know, all these creases, but this down here is still solid. All right, great. Now on the inside, I have drawn a horizontal axis down across the bottom here. So here's my windows that I had cut, but on the bottom I put my horizontal axis. Because what I'm going to do is I'm going to draw a approximation of the normal curve inside here. Now, this middle crease that's in the middle here, that's where the mean is located. Excuse me. And so that's going to be my highest point. I'm actually going to put a dot up there, just so I kind of know where I'm aiming for here. And then at each of these creases to the left and the right of the middle one, I'm going to have that be where my inflection points are. So about halfway up, I'm going to put a dot on each side. And what this does is just allows me a way to sort of draw my normal curve in here. Now I'm going to do it in pencil first because I want to make sure I do a good job. And I'm going to come up from the axis here to my inflection point, remembering that this is the part where it's concave up like a cup. Okay, and then once I get to this transition point, I know that's where it goes to concave down like a frown. And then it gets to this inflection point here, and it goes back to concave up like a cup, comes down to where it has an asymptote at the x-axis. And I did it in pencil first so that I could erase if I had any lines I didn't like, and I didn't like this line, so I'm gonna erase that. But I realize that it's hard for you guys to see that on the document camera, so I am going to go over it with my Sharpie. You can probably just leave it in pencil on yours because you're always going to be just looking at that on your own there. And that's my normal curve. And then I'm going to label some things on my normal curve. I know that this line right here, that's where mu is, okay? And so this first line over here, I know that that's mu plus a standard deviation. So I'm going to write mu plus sigma, okay? And over here, I'm going to write mu minus sigma, because that's one standard deviation below the mean. So one above, one below. And if you're thinking back to the previous video, hey, that's a z-score of +1. That's a z-score of -1. You would be correct. That's good thinking. Okay. Now, there's a rule in statistics. Our old book used to call it the empirical rule. This book calls it the 68, 95, 99.9% rule, which is a very accurate name, but it's a bit of a mouthful. But what it says is this, guys, is if we have data that we know is approximately normally distributed, then from one standard deviation below to one standard deviation above, that's where we would find 68% of all of our data. In other words, fold down that middle piece. And from this edge to this edge, that represents 68% of the data. And sometimes people like to have a little, they can copy the curve so that you can see 68% of the data there. All right. See how that works? Our little foldable then helps us. That's 68% of the data. If I go over the next crease here, that's actually the mean plus 2 standard deviations. And this one here is the mean minus 2 standard deviations. Okay. Well, guess what? If I close these windows, okay, remember the rule I said was 68, 95. That means we would have approximately 95% of all of our data between these two. And again, some people like to copy the curve up. That's fine. You can do that. Okay. Yeah, that's 95% of the data when you close those two windows. Okay. Well, remember the rule is 68, 95, 99.9%. Well, yeah. The next, or 99.7%, sorry. The next lines, fold down the last one. Well, that far edge, then that's mu plus 3 standard deviations. And this one over here is mu minus 3 standard deviations. And if we close those windows, okay, that's where 99.7% of all the data will be located. If the data is normally distributed. And again, you might want to, copy over your curve bit there if you want. That's up to you. All right. So our foldable then is designed to help us understand where data is located in the normal curve. And it's actually quite handy. So this is a foldable that I encourage you to keep with you if you're taking a test. This can come in very handy. If you're using it for the College Board exam, it's not a recommended or a specifically allowed tool, but hey, that's all right. We're okay with it, using it on our test. So let's just keep that between us, right? So a couple other things in here. If it's 68% in here, then how much is in each half, right? Remember, it's perfectly symmetrical, right? So 34% of the data is between mean and plus 1 standard deviation. 34% is between mu and minus 1 standard deviation. So thinking back to my US women that are approximately normally distributed in their heights, if you take 64 inches and add 2 inches and subtract 2 inches, that's between 62 inches and 66 inches. 68% of women are in that range. Okay, 34% above and 34% are below that by 2 inches. Now, if we want to go a little further out, okay, if we wanted to add 2 standard deviations, right, that's 95% of the data. Well, 68 of it's in between, so that leaves 27% evenly distributed between these two windows. So I know that this distance represents 13.5% of all data. And this distance is also 13.5% of all data. Okay. So yeah, if you're saying, oh, well, what percentage of women are between 66 and 68 inches tall? That's 13.5% of women in the US. Okay, now I'm using US women. It's different if you go to different countries. So that's That's a good thing to remember. Lastly, if you go to the remaining part, well, we're going from 95% to 99.7%. There's a 4.7% remaining. So it's symmetrical, right? So half of it here, 2.35%, and half of it's over here. And so we know, for example, if you go 2 standard deviations below the mean for US women, that's 60 inches, down to 3 standard deviations, okay, which is 58 inches. So what percentage of women are between 58 inches and 60 inches tall? That's 2.35%. So it's becoming a more rare occurrence, okay, because normally distributed data, there's less data for the further you go from the mean. So here's our normal distribution, along with our 68, 95, 99.7 rule. And you can see, as you lay out your foldable, then you can kind of figure out where this data is going to be located. And you can move from 2 standard deviations below to 1 standard deviation above. You can go to, you can move these around all you want, but this will help you remember that when you have data that's normally distributed, where can you find what percentage of the data? And I make that foldable with my students every year. It seems to help. I hope that helps you when you're looking at how to work with data that is approximately normally distributed. All right. We're going to transition back for just a second here. The stuff that we did previously with Z-scores, okay, is going to come into play here now with our normal distribution. Because while the foldable that we just made is handy, for sure, it's very handy, it deals with integer values of the Z-score, right? If you're at 1 standard deviation above the distribution's mean, that's a Z-score of 1. If you're at 2 standard deviations above, that's a Z-score of 2, 3, and so on, and -1 and -2, -3, which is fine. That's great. But what if your data point, when you find a Z-score, isn't actually on one of those? Can you still figure out a percentage of data that's below that or between 2 Z-scores? And that answer is yes. It's going to take us to our first table that we're going to use. You see, for my calculus folks, if you've had calculus already, I could give you the equation for that curve. In fact, we did see it when we were in calc last year or 2 years ago, depending on when you were in calculus. And we could find the area under the curve. Okay. Now, for you non-calculus folks, just disregard this next statement. Okay. That integral that we would have to do requires us to, it's an indefinite integral because it goes to infinity or negative infinity, depending on which side we're going. But you don't have to worry about that. Okay. Now, everybody back together. There's a table in the back of the book where all these areas have already been computed for you. And it's called the standard normal distribution. Okay. You see, the women that have a standard deviation of 2 and a mean of 64 would have one shape of a normal curve. US men, on the other hand, their distribution is different. There, the mean is 69 inches and the standard deviation is 2.5 inches. Okay, so now you're looking at a totally different normal curve. The peak has been moved over, the standard deviation is a little bit wider, so it would require a whole bunch of new calculations to compute the areas under the curve for that one. Okay, and then if we take something totally different that's normally distributed, and look at that, you'd have infinitely many situations where you would have a new normal curve. Well, the standard normal curve is for Z-scores because every data set can be brought back to the Z-scores. Okay, if you're depending on how tall you are right now. Okay, even though our data was for US women who are adults, let's say, some of you women are in the class are still growing. For the most part, though, by the time you're a senior, most women are done growing by the time they're 18. So you could actually compute your Z-score and use this information to probably find out, what percentage of women are taller than you or shorter than you or whatever. For the U.S. men, it's a little different because a lot of times the men in the U.S., you guys are 18 or 17, going on 18, you are probably not done growing yet. You probably have a little bit of growth left to do. While you're in college, you'll get a little bit taller, maybe. Not everybody, but it does happen a little bit more often for men. So you could find your Z-score and find your percentage right now, but using those statistics of 69 for the mean and 2.5 for the standard deviation, that might change for you, is what I'm saying. The women in the class probably not so much, not as much anyway. So what I'm going to do is look at a Z-score for my own height, and then we'll take a look at how I could figure out what percentage of men I'm taller than or shorter than, which is unfortunately a bigger number. Because my height, well, to be generous, I'll give myself a height of 5'7". Okay, so in other words, I'm 67 inches tall. All right. Now, the distribution for men's height in the US looks like this. The mean is 69 inches and the standard deviation 2.5. So my Z-score is going to be negative. Yes, it is. I know. Okay. Would look like that. Sorry, it's supposed to be 2.5 down there. And so I would have a Z-score of, let's see, -2 over 2.5 is -0.8. So I'm not on one of the standard deviation lines that are on my little foldable over there. Okay, so could I still figure out how tall I am relative to the peer group of US men? And that answer is yes. I would just need to know, I'm just going to do a quick sketch of a normal, so it's not going to look very good, guys. Told you. If this is the mean right here, that's a Z-score of 0. And here's the transition point. My Z-score is not quite there, right? Oh, sorry. I'm negative, I forgot. All right, so I'm over here. Thanks for reminding me. So there's my Z-score of -0.8. So maybe I want to know my percentile rank or the percentage of people I'm taller than. So that's what percentage of people are over there. That's what table A can tell us. So in your book, in the appendices, you've got different tables, and there's one called table A. So I'm going to switch over to my document camera, and we're going to look at table A together. I'm going to use the one out of the book for right now, and then later on, I'm going to show you another place you can get one. I'll probably show you that in class. So let me transition us over to the doc camera here. All right. So I am now in the appendix of our book, and I am on what's called, you can see at the top, table A. And so what I'm going to do is show you how table A works. You can kind of see at the top, it's telling you area. It says probability, guys. We'll talk more about why it's a probability later. And then they have all this data out here. Okay, well, what you do is you find the Z-score by looking down this column over here. And this will give you the Z-score to the 10th place. Okay. And then if you have 100ths, like in the case of my Z-score, right, it was only -0.8. So I'm just going to go down until I see -0.8. And then in the 100th place, I have it 0. So I'm going to zoom us in a little bit here. Apologize if that makes anybody feel seasick all of a sudden. And what I find in the first column is 21.19%. So a Z-score of -0.8 is greater than 21.19% of all scores. In other words, I'm taller than, well, just over 21% of US men. but we already knew Mr. A, not exactly tall. Now, if your Z-score, I'm going to scroll this up just a little bit here. If your Z-score has a value that's not 0 in the hundredths place, see how these columns all have headings that are got 100th on there? Well, then that is how you look up a 2-digit Z-score. So if I had a Z-score, let's just go to one that you can see, of like negative 2.64, I would go to negative 2.6 and go over to the column for 04, and look, that Z-score is greater than just 0.4% of data. Okay, so if I was 2.6 standard deviations below the mean for US men, okay, I would only be taller than 0.41% of men in the US. Now, we can actually figure that out, because remember, I said the mean was 69 inches minus 2.64 standard deviations. And that would be a man who is 62.4 inches tall. So just like 5'2" and a half. That's relatively short relative to US men. That's what that's saying. Okay. So that's how you look up data on table A. Now you might be going, well, hey, but I'm taller than average, Mr. Ray. Okay, I bet we have some students in the class right now who are, let's say, 6'2". Okay, if you are 6'2", if you're a man who's 6'2", okay, you are 74 inches tall. Okay, look at that. You are 2 standard deviations above the mean. Well, turn the page, and there's your standard normal probabilities for Z-scores that are above the mean. And if I go down to 2.0 right here, if you're in our class and you are 6'2", you are taller than 97.7% of men in the United States. So there we go. And if you have the columns again refer to the hundredths place. So you can figure out the various percentages in here. Oh, by the way, if you were a woman who's 6'2", I don't know if we have any of you in here. Okay, remember your mean was 64? Oh, whoops. Not divided by, I keep hitting divided by. Trying to hit minus. You are 10 inches taller than average with a standard deviation of 2. Your Z-score is 5. Guys, our Z-score table stops at 3.5. There's 3.4, go all the way to the last column. That's 3.49. You would be taller than 99.98% of US women at 3.5 standard deviations. At a standard deviation of 5, you are quite a bit taller than women. Yeah, it's like a negative. I'm sorry, it's a 0.00003. So it's really way small number that would be taller than you. And so yeah, you're quite a ways up there in terms of standard deviations above the mean if you're a 6'2" female. And if you think about that, that's why we notice women when they're, a woman who's 6'2" stands out in the crowd for sure. I mean, a man who's 6'2" is taller than 97% of men, so they stand out in the crowd as well. All right. Well, we will have more on this when we get to class. So come come back over here from the document camera. So thanks for watching, guys. If you're still confused or have questions, don't worry. We're going to talk about this a little bit more in class on Thursday or Friday, depending on when I see you. So, all right, thanks everybody, and we'll see you soon.